Okay, so this video is on section 4.2 part 3, where we're going to be calculating the actual area under a curve, or bounded by a curve in the x-axis over a closed interval. And in the last lesson, so in part 2 of section 4.2, we're approximating the area under the curve using rectangles and using different values on the subintervals created from deciding the number of rectangles that we're using in order to calculate the height of each rectangle. So we use the left endpoint of each subinterval, the right endpoint of each subinterval, and then we also calculated the lower sum approximation for area, where we chose the value on each subinterval that would use the smallest function value, right, or the lowest function value on each subinterval to calculate the height of each rectangle. And then also the upper sum, which uses the largest function value on each subinterval to calculate the height of each rectangle. So we were getting approximations, and we talked about whether we had over approximations or under approximations for each of those estimates of the area under the curve. And then in this lesson, we're going to begin talking about calculating the actual area. And we last class talked about, well, how could we get a better approximation of the area using that method of adding up the areas of rectangles? And you guys told me, well, we could use more rectangles, right? Like if we keep adding up or dividing up the interval over which we're calculating the area into more rectangles, that's going to give us a better approximation. So we could also think about, if we're creating more and more rectangles, well, that seems like the idea of a limit, and that's exactly where we're going. So in the beginning of this lesson, we're going to think about finding a lower sum to approximate the area of a region under a curve. And I have a picture here of a graph. So we're going to find a lower sum using n subintervals. So that means n number of rectangles. And we're calculating the lower sum. So that means that we want to use the minimum value of the function to calculate the height. Because this function is a decreasing function over the interval from 0 to 2, that means that the minimum value is going to correspond to the right endpoint of each subinterval. And that's the note that I have on here. And this is because this is a decreasing function on this interval. Okay, so in this picture here, I have labeled our delta x's, and it's over the interval from 0 to 2. So delta x will be equal to 2 minus 0 divided by n, the number of rectangles that we want to use. And we want to use n rectangles in this case. So that would simplify to be 2 over n. So delta x is equal to 2 over n. Now, if we're just focusing on the area of the first rectangle, right, that would be the area of the first rectangle would be the width of the rectangle times the height of the rectangle. The width of the rectangle will be delta x. We already have that there. And then the height would be, in this case, looking here, right, if we're using the lower sum, and we said because it's a decreasing function, we're using the right endpoint of each subinterval to calculate the height. So the height of the rectangle would be f of delta x. Well, another way to write that, since we have a different representation of delta x, would be f of 2 over n times 2 over n. Okay, so then let's look at calculating the area of the second rectangle. Well, using the right endpoint again, so this point up here, that would actually end up being f of 2 times delta x, right? 2 times delta x. This is the second rectangle. And then we could rewrite that product to f of 2 times delta x times delta x. We could rewrite that as f of 4 over n, right? 2 times 2 over n times 2 over n, replacing that delta x. So the lower sum would come from adding up all of those products, the n number of products, which would, each of those products represents the area of each rectangle. So this first product is that first, the area of the first rectangle, so f of 2 over n times 2 over n plus f of 4 over n times 2 over n. And then the last rectangle, since we're finding the lower sum and we're using the right endpoint to calculate the height of each rectangle, that means that for the last rectangle, which there would be n number of rectangles, would end up being, the height would be f of 2, right? The right endpoint of that last subinterval, times 2 over n. So times delta x. So this is again lower sum, right? Lowercase s. That means we're calculating the lower sum. And we want to rewrite this sum in sigma notation. Okay, so with I being equal to 1, up to n number of rectangles. So let's think about how we could rewrite the rule that would represent this sum, using I as our index. So for evaluating our function, we could think of I as being 1 for the first rectangle, I as being 2 for the second rectangle, I as being 3 for the third rectangle, all the way up to n number of rectangles, right? So f of the height of each rectangle would be f of 2I over n, and that's just delta x times I. Since we're using the right endpoint of each subinterval. So that the height would always be the function evaluated at delta x times I. And then delta x, again, is still 2 over n. Okay, so we want to simplify this. We have those summation rules. We want to simplify this a bit. So that we can use this to help us with approximating the area under the curve with n rectangles. Okay, so just replacing f of 2I over n. So since the equation of this function is, oh, I should have put the equation on here. I'm sorry. So since the equation of this function, f of x, is equal to 9 minus x squared, replacing f with this rule, so replacing the x with 2I over n, this is just f of 2I over n. Okay. Squaring the 2I over n, that becomes 9 minus 4I squared over n squared. Okay, and then we can think about distributing 2 over n. And that gives us 18 over n minus 8I squared divided by n cubed. So now we're going to use the fact that we can rewrite, we have a difference here. So we can rewrite this as a difference of the sums. But also in this next step, I'm going to pull out what could be thought of as the constant. So the parts with n that are constants. So that then we can just think about using our summation formulas in order to rewrite the sums that are written in sigma notation. Okay, so we can treat 1 over n and 8 over n cubed as constants, right? Because if you were to assign a number of rectangles, so like set n equal to 4, n equal to 6, or n equal to 100, you would end up being able to pull out that constant in order to evaluate the sum. So we're able to treat n as a constant. Okay, where now we can think about using those summation formulas that I told you I would give you to rewrite that sum and that sum. The constant, so that would be 1 over n, and then to rewrite the sum for I equals 1 up to n of 18, we can just multiply 18 by n. Okay, and then using the formula for I squared, that would be n times n plus 1 times 2n plus 1 divided by 6. And then just to simplify this a bit, we can, what color do I want to use here? I'll use green. We can divide those n's out. This n will cancel with one of these n's. And then 8 over 6, that can become 4 over 3. So that's how we end up with the 4 over 3n squared. So 18 minus 4 over 3n squared. And then we just want to multiply out that product here, n plus 1 times 2n plus 1. And that becomes 2n squared plus 3n plus 1. And distributing, we end up with 18 minus, what does that become? 8 thirds, because the n squareds will cancel. So minus 8 thirds, and then plus 4 over n, because the n's will cancel, the 3's cancel, and we're left with 1 n in the denominator. And then just minus 4 over 3n squared. And we can clean that up a little bit more, just combining like terms. So 18 minus 8 thirds, that will be 46 thirds plus 4 over n minus 4 over 3n squared. Okay. And depending on, so this is our lower sum formula. This is the formula we could use to calculate the lower sum for n number of rectangles. So you could assign values to n here, but we're going to do something else with this formula. We did not calculate the upper sum. In this case, it would be using the left endpoints of each subinterval. I'm just going to give you what the upper sum formula would be for n rectangles for this particular function over this particular interval. It would be very similar. It would be 46 thirds. Oh, I'm sorry. This should have been minus. Whoops. Going back. That should have been minus. So sorry. Yeah, when we distribute, that should have been minus. So this, for the upper sum, should be 46 thirds plus 4 over n plus 4 over 3n squared. So that's our upper sum. We have our lower sum and our upper sum. So using your graphing calculator now, I want you to type in the rule. So in y sub 1, go ahead and type in your lower sum formula. Obviously, you're using x's instead of n's. Do not use the fraction bar. Use parentheses, and be very careful about your use of parentheses. So when you type in this last term, you would use parentheses 4 divided by, and then use parentheses around the denominator 3n squared, and close the overall parentheses for the fraction. So just be very careful about that. Make sure you're using your parentheses appropriately, but use your parentheses so that you're getting decimal approximations in the table. We're going to be examining the table, and we want the decimal approximations instead of the fractions. If you use the fraction bar, it's going to give you fractions in your table. So use parentheses and then type in the upper sum, and again, the argument, instead of n's, you're going to be using x's, into y sub 2. And then making sure that you have your table set so that you can type in values for x. Go ahead and hit second window so that you pull up the table set menu, and make sure that under independent, ask is highlighted. That's going to allow you to type in values for x. So then you can hit second graph to go to the table and go ahead and fill in all of these values. So for y sub 1, for 10, I see why am I under the highlighter? I see 14.92. For 20, I get 15.13. For 50, I get 15.253. For 90, I get 15.289. For 200, I get 15.313. For 1,000, I get 15.329. And for 5,000, I get 15.333. And then filling in the table for y sub 2, for 10, I get 15.747. For 20, I get 15.537. And for 50, I get 15, or that was for 20, so 50, I get 15.414. For 90, I get 15.378. For 100, I get 15.373. For 1,000, I get 15.33. Oh no, I'm reading. Yeah, 337. Sorry, you guys. I'm trying to look across here. So I get 15. Oh, I wrote the wrong value for 200. Sorry. So 90 was 15.378. I had that correct. And then for 200, I get 15.353. And 1,000, I get 15.337. 5,000, I get 15.334. Okay. So y sub 1 again was our lower sum, and then y sub 2 was our upper sum. So these different values of x represent using different numbers of rectangles to approximate the area under the curve, bounded by the curve, the x-axis, and on the interval from 0 to 2. So our lower sum approximation for 10 rectangles would be 14.92 approximately. Our upper sum approximation would be 15.747. And then notice what's happening as we're using more and more rectangles. It seems like the lower sum is approaching the same value as the upper sum, right? As we're using more and more rectangles, so you could think about that as n is approaching infinity, right? As we're approaching infinitely many rectangles, it seems like that lower sum is approaching 15.3 repeating. And it also seems like the upper sum is approaching 15.3 repeating. And we get to, oh, if I keep going, so if I put in, if I put in like 100,000, then they were both reading on this table 15.333. So it seems like as n is approaching infinity, the lower sum and the upper sum are both approaching 15.3 repeating. Well, so what does this mean? Our conclusion. So to summarize, both the lower and upper sum have a limit as n approaches infinity. So we could write that with limit notation. The limit as n approaches infinity of the lower sum is equal to the limit as n approaches infinity of our upper sum. And that limit is equal to 15.3 repeating. What does that number represent? What are we doing with these values, right? We're thinking about adding up infinitely many rectangles in order to find the area under the curve or bounded by the curve in the x-axis on the interval from 0 to 2 in this specific case. So these limits represent the area of the region. So the area, the actual area under the curve here, this area is 15.3 repeating. And if you use the lower sum formula and choose a number of rectangles, that'll give you an approximation, an underestimate of the area, or an under approximation. And if you were to plug in a number into your upper sum, that would give you an overestimate of an overestimate or over approximation of the area. But if we think about taking the limit as n approaches infinity, then that gives us the actual area under the curve. Okay, so let's come up with a more formal way of calculating, or a more generalized way of calculating the area of a plane region. The plane region is just the area under the curve bounded by the x-axis and then on that interval, on a closed interval. Okay, so in this picture, we have some rectangles drawn, but notice that the height of each rectangle is not determined just by a left endpoint or just by a right endpoint, or even not necessarily like the largest function value, right? So it's just choosing random x values on each subinterval in order to find the height of each rectangle. And that's okay, that's allowed. So this is choosing random. So choose random x values on each subinterval to find the height of each rectangle. So in that case, the sum of the areas of n rectangles, right, would be delta x times the sum of each of the heights of the rectangles. And in summation notation or sigma notation, that would be represented like so. Well, we just discovered if we take the limit, like we think about using infinitely many rectangles, that ends up being equal to the area of the region that we're trying to calculate area for. So if you take the limit as n approaches infinity of this sum, or of the lower sum, or of the upper sum, that's equal to the area of the region. But how do we come up with this? Like, how do we take this limit for any given function over a closed interval? These formulas will be helpful for us using this limit definition. This is our limit definition of area of a region under a curve, bounded by a curve in the x-axis over a closed interval. So delta x will always be b minus a divided by n. And then, so those delta x, remember, represents the width of each rectangle. And then if you choose the right endpoint of each subinterval, then you could replace c sub I as a plus I delta x. So taking the first endpoint of the interval over which you're calculating, and then if you add delta x, right, like just delta x, that would give you the right endpoint of the first rectangle. And then if you keep multiplying delta x by whatever I is, so the number of rectangles in that you are, then that'll keep giving you the right endpoint of each subinterval. So, and we're using the right endpoints here so that we can let I, this allows in our summation notation to let I be equal to 1. It's a little bit trickier if you use the left endpoint, and then I would be equal to 0. But because our summation formulas that we use are all with I being equal to 1. So you would have to end up rewriting and think about like shifting the sum over in order to use your summation formula. So it's easier to do it this way and think about the right endpoint of each subinterval as being used to calculate the height of each rectangle. By the way, this was proved by Riemann. And we're if you've looked ahead at all, you've seen the name Riemann before. So this was proved by Riemann. His name will come up again. Okay, so I have the work all written up for this first example. So if we want to calculate the area bounded between f of x equals to 9 minus x squared and the x-axis on the interval from 1 to 3, using those formulas above, delta x for n number of rectangles would be 2 over n. And then c sub I would be 1 plus, so 1 is the value of a, right? The first endpoint of the interval that we're calculating area over, plus delta x times I, which is 1 plus 2i over n. Okay, so area is going to be equal to the limit as n approaches infinity of this sum. And we have to rewrite this sum in order to take the limit. So replacing with the rule here for f of x, and then multiplying out 1 plus 2i over n squared. This is what we get here. And then distributing that negative and combining like terms. Here we are. And then we're going to think about distributing 2 over n. So distributing delta x. And that leaves us with 16 over n minus ai over n minus ai squared over n squared. So we have some differences here. And we can rewrite the sum. We're allowed to rewrite the sum, right? The differences. And we're again going to pull n out as a constant. Because remember, if we were to assign a number, right? A number of rectangles, then we would be able to treat it like a constant. So we're able to treat it like a constant here. So that's why we're able to pull out the 1 over n 8 over n squared. What happened? 1 over n. Do I have a typo? I think I have a typo here. Sorry, you guys. Just double check this. That should have been n squared. Sorry, you guys. And then this should have been n cubed. Silly me, whenever I distribute that in. I will try and fix that. But the next line is correct, right? We should have then pulled out 8 over n squared and 8 over n cubed. Okay, so we're okay. And then we know the summation formulas for evaluating each of these sums. So replacing those sums with the summation formulas, we have 16n. We would have n times the quantity n plus 1 over 2, and times n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. And then from there, simplifying, those n's cancel in that first product. We would have minus 4 times the quantity n plus 1 divided by n, minus 4/3 times n plus 1 times 2n plus 1, all divided by n squared. And then we could multiply out that numerator in order to get the 2n squared plus 3n plus 1. And at this point, we are ready to take the limit as n approaches infinity. You guys know how to take the limit as n approaches infinity. And we can think about taking the limit of each term here, or each product, right? Like the limit as n approaches infinity of 16 would just be 16. Right? This just goes to 16. The limit as n approaches infinity of n plus 1 over n, that minus 4 will be there. Well, this would just be 1, right? Think n behavior model, that would just be 1. And then 4/3 will be there, minus 4/3 will be there, and the limit as n approaches infinity of this will be the n squares. Think n behavior model. The n squareds would cancel, and it would just be 2. So we end up with 16 minus 4 times 1 minus 4/3 times 2, which is 16 minus 4 minus 8/3, or 28/3. So the area under the curve, or bounded by the curve and the x-axis on the interval from 1 to 3, here would be, the exact area would be 28/3. This is our area. So if you want to pause, I'm going to actually work through this next example, but if you want to pause the video and try this one on your own and then come back to check it, go for it. If you feel like you're not really ready for that yet, then you could kind of go like step by step, or pause and see if you can do the next step, just referencing the example above. Okay, so first we need what delta x would be for this function over this interval. So delta x, the interval is from 0 to 1, so that'll be 1 minus 0 divided by n, or just 1 over n. C sub I would be 0 plus delta x times I, which would be I over n. So C sub I will actually just be I over n. So our area would be equal to the limit as n approaches infinity of the sum from 1 to n of, I'm just going to go directly to using the rule. For f, it would be I over n squared plus 2 times, or here I should use an extra pair. So times 1 over n. I could have used parentheses. And then I'm going to think about distributing. Well, actually, before I think about distributing, I'm going to multiply this and then distribute the 1 over n. So this will be equal to the limit as n approaches infinity so this becomes I squared over n squared plus 4 times 1 over n. All of this should be in brackets here. And now I can think about distributing the 1 over n. Make sure you are writing your limit for each step until you actually think about taking the limit as n approaches infinity. Okay, so this will be I squared over n cubed plus 4 over n. And now I will split up that sum of sums. So we have, and I'll pull out n because that can be treated as a constant. So it'll be 1 over n cubed times the sum from 1 to n of I squared. And I have the summation formula for that. And then pulling out the 1 over n. And I have the summation formula for the constant. So the limit as n approaches infinity of 1 over n cubed, the summation formula for I squared I just had it here, but I want to make sure I'm using the correct one. There it is. N times n plus 1 times 2n plus 1 divided by 6. And then plus 1 over n times 4n. And I want to simplify that before I think about taking the limit. So this n will cancel with one of these n's. These n's will cancel. So we're taking the limit as n approaches infinity of n plus, I'm going to multiply that numerator out actually. So 2n squared plus 3n plus 1 over 6n squared plus 4. And then when we think about taking the limit as n approaches infinity of this first fraction here, thinking n behavior model, n squareds would cancel, so that limit would go to 1/3. And then the limit as n approaches infinity of 4 would just be 4. So this limit ends up being equal to 1/3 plus 4, which would be 13/3. Is that right? My note. Give me just 1 second here. My notes cut off. That's supposed to be 4. Where did 4 come from? I'm sorry, you guys. This should have been a 2. I don't know where the 4 came from. That should have been a 2. So this limit goes to 2. I knew that seemed off. So 1/3 plus 2 would be 7/3. So 7/3 is the area bounded by the curve by f of x and the x-axis on the interval from 0 to 1.